So now's the discussion session. I'm Tom Otto from NTHU. There are many experts in this conference, and so I thought rather than I present discussion items, I listed the questions that I would like to ask to experts. So it'd be nice if you can give me some thoughts and comments. And I listed, these are my random thoughts, and I also appreciate good discussion with Tetsuya-san about discussion session. Then the first item is, so we have heard, many of you, that there's a new era of thousands of mostly localized FRB is coming. Chime has outriggers, craft miniature, DS2000 is coming, Casata, Burst, Quartz, SK, Cosmic Antenna, many projects are finding more and more FRBs. So then, like Stefan's talk, gave a great talk. How do we get the spec Z for this many sources? First, number is too many, and also there are more distant faint sources. And can we get all spec Z? If not, how do we make maximum use of this data with photometric redshift? So these are the things that I'm wondering. Second topic, I came up with simultaneous or much messenger observation, which also we have many times in this conference. For this, good planning of coordinated observation and collaboration may be needed. For example, there were excellent talk about high-speed optical camera simultaneous observations, or X-ray simultaneous observation, like this 1935. So these, if we coordinate our efforts, that would be probably maximize our chance to do a good science. And not just the multi-wavelengths, in terms of frequency dimension, that our radio telescopes also have different frequency coverage. For example, the Burst telescope has 300 to 800 megahertz, but some other telescope goes to gigahertz ranges. So it'll be nice to some sort of sharing information on the open opportunity to simultaneous observations. And also, this is particularly for Burst project, we are looking for a north-south international collaboration to put out rigor stations. So to sum up, so now instead of a few cute FRBs, we are coming into the era of thousands of cute FRBs. So how do we prepare for this? So that's what I wanted to discuss. And then hand this over to
Thanks. Yes, I wanted to be a bit more oriented on the instrumentation, just taking ideas from what I have heard, many very interesting things in the past 3 days. Up there is a list of what we would like to have from a generic instrument, very high sensitivity to capture high redshift sources for many reasons, and many talks discussed about that, cosmology, H0, baryon density, as well as for studying close-by repeaters for interpreting their nature. We also want high sensitivity and a large field of view to capture the bulk of the population at a low zeta, again for interpreting the FRB machine, as well as studying galactic halos, intervening IGN, and so on. We also would like to have astrometric localization for upper limits, for allowing for upper limits on counterparts or detecting them, long exposure for addressing the issue of repeaters and not repeaters, apparent not repeaters, large bandwidth for studying scattering while being able to keep a decent level of detectability of the sources and constraining the spectra, very high time resolution, especially to study emission mechanisms and comparing with other kind of sources. So there are a lot of experiments now running. This is not an exhaustive list. If I missed some of your favorite experiments, sorry about that. That was not intentional. And there are several other experiments about to be launched or under design, as those we heard about this morning. Now, addressing the full list of these desires is creating a dream instrument, which will be hard to be really be able to assemble in reality. So we need to find a compromise, and the question is which is the best deal. So I left the 3 questions for you to meditate if you want. On one side, is it possible to coordinate the design of a new instrument to maximize the synergies among them, complementarities, avoiding duplications, for instance? Is it possible to do something similar on the software side for not having to reinvent at any time suites which are already available elsewhere, but maybe just improving on them? Also, there is the other important instrumental aspect here, which is related to the follow-ups, multi-wavelength follow-ups, of course for statistical association of the FRB to a given population, or for cosmological studies. And we had examples in the talks of previous days about the importance, for instance, of quasi-simultaneous coverage in X-ray, ultraviolet, and other wavelength. So how can we really optimize all these things, organizing a global approach to this problem, which will become really a tough problem when we will have thousands or tens of thousands of objects to be followed up. So these are, I think, key questions. I don't know if we'll be able to solve all of them today, I don't think. If not, maybe we can find another option for meeting and addressing this, just a spot of a meeting next year in Sardinia, which will be basically devoted to all time domain activities.
Okay, so earlier in the week I talked to you a bit about the challenges I think we face when it comes to getting redshifts for any single host galaxies, particularly as we get to redshift 1 and beyond. Just today, of course, we heard about the bigger challenge is going to be what happens when the tsunami of localized FRBs, localized host galaxies, starts to emerge from these surveys. It's a fantastic problem to have, but how are we going to tackle that? So just to give you an idea, the existing craft, ASCAP, that's the Incoherent Sum Survey, and with the recent introduction of Krakow, fewer than 10% of those host galaxies that we went to look at had a catalogue redshift. So 90% of the world, we had to go away and get our own redshifts for those sources. And that wasn't a particularly deep survey. Indeed, most of the host galaxies that are redshifts beyond about 0.5 simply don't show up in existing archival imaging, Ham stars, Sloan, etc. You go a little bit further with the dark energy camera that covers the south very well, but not completely. And so ultimately, that's why we've had, within the craft, we've had to take advantage of our access to the wonderful ESO facilities to do our own 8-meter class follow-up, and doing that collaboratively as well with the F4 group to get access to CAT, Gemini, and so on. Of course, as we go to fainter magnitude limits, potentially more higher redshift objects, source confusion, even at subarc second localization, means host associations are potentially even less certain. So there are particular challenges I pointed to earlier with trying to get redshifts between about 1 and 3. So the key emission features that we tend to rely upon as optical redshift astronomers, things like the oxygen 2 doublet, 3727, all the way up to H alpha, they begin to be moved into these windows, well actually not windows, they're like doors, regions of quite high carbon dioxide, water vapor absorption in our atmosphere. And so that makes it particularly challenging to be able to observe from the ground. As if that wasn't enough, you then got a forest of these OH emission features as well, which further complicates searches for faint emission line objects. So this is a well-known problem already in galaxy redshift surveys, not just FRBs, the so-called redshift desert between about 1 and 3. It's one of the reasons you don't find many redshift surveys being done in that region, because it's hard. But actually, those sorts of redshifts, all is not lost. So there are some other ways that we can try to get redshifts, at least for individual objects, maybe not for very large ensembles. But for instance, the CO transition, CO molecules, which are in common galaxies, they actually become, well, they're redshifted, that means they come to lower frequencies, down into the shorter wavelength bands of Alma. So just to give you an example, for a given redshift of your host galaxy, these are where the CO features extend and then cover, and these are the individual Alma bands. And so for CO1 to 0, even out to redshift of 2, you might be able to pick up the fundamental line, you might be able to get the next highest order lines, potentially sometimes even these other lines, although they obviously get weaker, but they might also then, for a given redshift, might be moved into the region of interest. So it's possible, but it would still be extremely time consuming to get redshifts for objects in that sort of 1 to 3 regime. Now, further down the track, we're about to see the start of the Rubin Observatory's legacy survey of space and time. So I don't know if you've seen the recent media release, but we have had first photons through the Rubin Observatory in Chile. Not first light, they will come next year, but the first photons, we now have a complete Rubin Observatory telescope, and so finally we'll have be able to start the long-planned legacy survey of space and time, that over the course of 10 years will build up very deep images through repeat visits. Of course, that'll be great for finding transients, not so great necessarily for finding fast radio bursts, but ultimately we should end up with the ability to determine photometric redshifts. Probably it will take at least 5 years and ultimately the full 10-year survey before we'll get a really good handle on the measurements from that. But the goal will be exactly to try and get redshifts to something like 0.5, 0.5% of 1 plus Z. So it'd be fantastic for them to do that. It's probably going to need lots of other additional data sets and training to go with it. That's what they're aiming for, such that would cover at least the entire southern sky and a fair way into the north. In the meantime, though, we'll have Euclid, of course, is already in orbit, and it's capable of doing slitless spectroscopy of emission line galaxies. They're also trying to do photo redshifts, albeit they don't have the same number of filters and bands that, say, Rubin will have. But by looking at structures in known clusters, they're trying to constrain at least groups of redshifts that way. We've got Spheric satellite being launched next year, and it will be observing something like 500 million galaxies through effectively 100 different filters. So you should be able to get pretty good photometric redshifts that way. And while this is going on, we will still have the DESI in the north, the new 4-meter telescope, the repurposed VISTA telescope at ESO will be switching to fully multi-object spectroscopy mode next year. There'll be a new instrument on the VLT called MOONS for multi-object spectroscopy. Of course, as KG told us, the prime focus spectrograph PFS on Subaru is undergoing commissioning. We're still hopeful that at some point in the future there'll be one or both of the Mauna Kea Spectroscopic Explorer or the Wide Field Spectroscopic Telescope that we talked about in ESO. They're collectively hopeful we'll continue to add spectroscopic redshifts that will be available to us. But we shouldn't imagine for a minute that every time we find a new localized fast radio burst, we'll be able to go straight to a catalogue online and get a redshift for it straight away. Maybe hopefully a reasonably good photometric redshift. But I have to say the photometric redshifts that we have had access to in the Kraft era have not been particularly good. The spectroscopic redshifts that we've got have been often well outside the so-called uncertainties on those values. So we have certainly got to work cut out for us in the future. It's an exciting time. Obviously, this is a good problem to have to know that we're on the cusp. We've been able to get potentially not just localised FRBs, but redshift for so many of them, but it's not going to come easy. Okay, so these are the questions that we would like you at each of your tables to discuss over the next 20 minutes, shall we say. So, for instance, in terms of what redshifts are cosmologically interesting. Now, I know this is very highly dependent on your favourite science case, but it would really help us to know where we should sort of focus our efforts. What redshifts are the ones we should be particularly pushing to get? And indeed, what other ways perhaps we haven't mentioned already that could be used to obtain redshifts for the hundreds initially, but thousands of FRB hosts, which are going to be spread across the whole sky. So traditionally, some of the other areas of science, they can say, well, we have 400 objects within a 2 square degree field of view, and we can go straight to the 2D spectrograph and AT. We can get all the redshifts in one observation. But because the way that we find these things turn up, there is no, at the moment, so little concentration of sources that we are pretty forced to go after them one at a time. And as already been mentioned though, what could we do to optimise the organisation of multi-wavelength follow-up, and whether it be through direct follow-up observations or indeed by real-time shadowing. And then of course, ultimately we might have to make some trade-offs. So what are the trade-offs you would be prepared to make between, say, your host galaxy sample size, the redshift accuracy for each one of those, and sky coverage? So for instance, would you be better off having, say, 1,000 FRBs with redshifts good to 1%, or 50,000 localised FRBs, but each of them, the redshift was only good to say 5%? Would you still get to your science goal that way? And then of course there's been, how do we coordinate the design of the new instruments and their software, of course, which arguably is just as important as the hardware, to try and maximise the synergies and the complementarities between them. So we'd like to invite you now to start discussing around your table your favourite answers to some of these questions, and then we'll reconvene at 3:25 and we'll go around and get you to provide some insights that hopefully will generate more discussion throughout this week.